So subject MISB 201 Advanced Business Analytics. So the activity provides dataset. So dataset that focuses on smart home device usage. So key points of the dataset, we have user behavior, how people interact with their smartphone devices, device efficiency, how well the devices perform in terms of energy consumption, user preferences, what kind of devices and features people like, and last, malfunction incidents, issues with the devices. So we have features. So the user ID, a unique identifier for each individual user. We have device type, categorical data specifying the type of smart home device. Usage hours per day, numerical data representing the various delay usage hours. Energy consumption, numerical data indicating delay energy consumption in kilowatt hour. Categorical data representing user preferences for device usage, low or high. Malfunction incidents, numerical data representing the number of reported malfunctions. Data age months, numerical data indicating the device age in months. And last, smart home efficiency, target variable in binary classification, 0 for inefficient, 1 for efficient. So, so from the dataset, so initial observations of the dataset appears suitable for predictive modeling to determine the efficiency of smart home device based on various factors. So potential correlations between features like energy consumption, usage hours per day, and smart home efficiency could be explored. Outlier analysis might be necessary for features like usage hours per day and energy consumption. Features engineering could be considered to create new features such as usage per kilowatt or malfunction rate. So uh, from the code, so there's the Python code. So Python code was generated from the dataset above. So lines 1 to 4, we have pandas used for data manipulation and creating data frames. Sklearn model, that model underscore selection used for splitting data into training and testing sets. Sklearn.tree used for building decision tree models. Sklearn.matrix used for evaluating models performance or mean squared error and R squared. So lines 7 to 16. So it defines dictionary data containing sample data for smart home devices. Its K represents a feature and values are list containing data points for each user. So for line 19, converts the dictionary data into pandas data frame and named DF. So line 23 uses one hot encoding to convert the categorical device type feature into numerical columns that is necessary for the decision tree model to handle categorical data. So line 25 to 27 separates features or all columns except user ID and smart home efficiency into X and target variable, smart home efficiency into Y. So lines 29 to 31 splits X and Y into training and testing sets using trend underscore test split. So the test size is set to 20% with random state of 42 for reproducibility. So lines 32 to 34 initializes a decision tree regressor with a random state of 42 and trains it on the training data. So line 37 uses the train model to predict efficiency for testing data and stores the result in Y. So line 39 to 42 calculates mean squared error or MSE and R squared score to evaluate the model's performance on predicting efficiency for unseen data. So lines 47 to 52 extracts feature importance from trained model. These values indicate how much each feature contributes to the model's predictions. So lines 49 to 51 creates a dictionary importance to map features names and their corresponding importance scores. So 50 to 52 prints the features importance. So overall, the code demonstrates a basic examples of using a decision tree regression for small home device efficiency prediction. It includes essential steps like data processing, training, evaluation, and analyzing the feature importance. So the output of the Python idle. So you have a mean squared error of 0.5 and R squared score of 0.0. So here are the list of the values from the output. So the independent variable. So in the model, the independent variable are the usage hours per day, energy consumption, user preferences, malfunction incidents, device age months, device type lights, device type security systems, device type smart speaker, and device type the thermostat. These variables are used in input to the model to predict the dependent variable, which is the smart home efficiency. So dependent variable y. The dependent variable y in the model is the smart home efficiency. The mean squared error or MSE value is 0.5. This indicates that the average squared difference between the predictive and actual values of the smart home efficiency. So to improve the model, the MSA should be reduced. So identify the MSA is identify the MSA is lower and or higher MSA. So an MSA of 0.5 indicates that on average your model's predictions are off by the square root of 0.5, approximately 0.71 units from the actual values. This is quite high and suggests that model is not performing well. So a lower MSA is always better. So a lower MSA indicates that the model's predictions are closer to the actual values, suggesting a better fit. While higher MSA indicates that model's predictions are farther than the actual values, suggesting a poorer fit. So interpret the MSA. So in the case with MSA 0.5, there is a significant room for improvement. So lower MSE is better. This indicates that model's predictions are closer to the actual values. So linear regression. So linear regression is a statistical method used to model the relationship between dependent variable or target variable and the one or more independent variable or predictor variable. It assumes a linear relationship between variables and aims to find the best fitting line or hyperlane in case of multiple independent variables. That minimizes the difference between predicted and actual values. So here is the code of the program. So lines 1 to 4. So pandas used for manipulation and creating data frames. So line number 2 used for splitting data into trainings and testing sets. Line number 3 used for building linear regression models. Line number 4 used for evaluating model performance, mean, squared error, and R squared. So lines 6 to 16 defines a dictionary data contains sample data for smart home devices. Each K represents a feature and value are lists containing data points for each user. So line 18 converts the data dictionary into pandas data frame named DF. So lines 22 to 24 uses one HATS coding to convert the categorical device type feature into numerical columns. So lines 25 to 28 separate features X and target variables smart home efficiency from DF. Split X and Y into training and testing sets using trains underscore test underscore split. So training models lines 32 to 34 initializes a linear regression models and trains into a training data. So line 37 uses the train model to predict efficiency for testing data and stores the results. Line 39 to 42 calculates the mean squared error or MSE and the R squared score to evaluate model performance. So lines 46 to 52 extracts the coefficient from train model representing the impact of each feature on the prediction. Creates a dictionary to map features name with corresponding coefficients and prints the feature coefficients. So here is the output of the Python idle. So the MSE is 0.62054. So this value indicates that the average square difference between the predicted and actual values of the smart home efficiency. A lower MSE is better, signifying model that makes more accurate predictions. In this case, the MSE is relatively high, suggesting that model's predictions are not very close to actual values. So R squared score is 0.0. This metric represents the proportion of variance in the dependent variable smart home efficiency that is explained by the independent variables. An R squared score of 0 indicates that the model explains none of the variability in the data. This is very poor result and suggests that the model is not effective at predicting smart home efficiency. So C, identify your independent variable X. So in the linear regression model, the independent variable X are the features. We have these independent variables are usage hours per day, energy consumption, user preferences, malfunction incidents, device age months, device type lights, device type security systems, and device type smart speaker. And last, we have device type thermostat. And we have the dependent variable. So the dependent variable Y in the model is the smart home efficiency, while the mean squared error value is 0.62054. So this value represents the average square difference between the predicted and the actual values of the smart home efficiency. So the MSE is higher. So identify if the MSE is lower or higher. So MSE is higher. Lower MSE indicates better fit. So since MSE of the value 0.62054 is relatively high, it suggests that the model is not accurate predicting the smart home efficiency. So interpreting the MSE. So the mean squared error is a metric used to evaluate the performance of regression model. It is measured the average square difference between predicted and actual values. So in the model, so the MSE is 0.62054. So this means that the average on the average the square difference between the model's prediction and actual home efficiency values is about 0.62. So identify which is better between decision tree regressor and linear regression based on the MSE results. So the decision tree regressor is better in the context it has a lower MSE of 0.5 compared to the linear regression model, which is 0.6205. So a lower MSE indicates that the model's predictions are closer to the actual values, suggesting better performance. So that's all. Thank you.